So hi, this is a video I wanted to make a long time, and it's also interesting for me and for you, I hope. And it's about the slew rate of an operational amplifier. And the concept of slew rate is, I think it goes beyond operational amplifier, op-amp, but I think at least in op-amp it's useful. And as I have seen another video on YouTube today, and there was an example of a datasheet, and there was written that some electrical component had a slew rate. So let's first write it down. It's called, this pen does not write anymore. Let's make it right first. Slew rate. You can read that, yeah. And that electrical component had a slew rate of 0.5 volts per microsecond. 0.5 volts per microsecond. So, what does that mean? Pretty easy. That means if you have a diagram where you have the time moving forward, and so this axis is the time, and then you have on the other axis you have the voltage. Then that means that the voltage can only climb as fast as 0.5 volts per microsecond. So let's imagine that the voltage rises in such a way. And so let's imagine that, for example, let's draw here an imaginary line. And let's say that this point in time here is 1 microsecond. And let's say that the device we are looking at has now, its output has a rise over time on the output, and the rise of the output, so let's say this is VO for V output of the device. And let's say in 1 microsecond, our device has risen from, let's say 0, it started at 0 volts, and it's risen to this point. Let's say this is, let's say 0.25 volts. So to a quarter of a volt it has risen, and that's what we really wanted. Let's mark that voltage line here, and that's really what we wanted from our device. But it could have risen even faster. We could have given it an even much more sophisticated task. Let's say, so this is around 0.9, so we'll land at 0.8 here. So this is 0.5 volts here. We draw that line. Hopefully I can draw a straight line. That's a little bit late. Our device could even have over time have risen faster. So it could have risen. This is not drawn good. It could have also risen in this 1 microsecond up to 0.5 volts, up to here. But yeah, we didn't put such a challenge on the device. Its only task was to rise a quarter of a volt and not half a volt in 1 microsecond. But if somebody wanted the device on the output to rise to 1 volt in a microsecond, that would be a much steeper line here. Perhaps we draw it in red, so we signal that this is not possible. So double, so we will end up around here, and this would be raised like this. Somebody wanted our device to rise to 1 volt, and we can see that that would not work, because then we can only rise as fast as 0.5 volts on the output of our device. And let's say that is our device here, some kind of integrated circuit IC, a red IC on it. And then you have some feed going out of the IC. Let's say that this here is V out. And why would V out go up in voltage? Let's say we have here coming in a V in, and depending on the input voltage there will be some output voltage, and perhaps that also rises the input voltage or any pattern, and we wanted to double the rise of the input voltage to the output voltage, or anything. It could have any IC, and it could have any, at least it has an output, and then the slew rate tells how fast the output voltage can change. In this case it's 0.5 volts per microsecond. And now the interesting part is, what if our output somehow is not used to go up linearly like this, but often what I have, at least in some of my circuits, is that you have some kind of device. Let's do again the next IC device here. This is the second IC here, and you have some voltage coming in, V in, and then you have here a V out. And oftentimes what goes into this IC here is not a linear or a constant voltage, rising or falling or being constant, but oftentimes it's kind of a frequency voltage, like so. And I have bad drawing of a sine wave, but let's just imagine for 1 second that this would be a sine wave. And then also some of these integrated circuits, they do things to this input sine wave voltage. So if that is here V in, and that is the time, and then sometimes, let's be a little bit more correct here, let's draw straight lines. And then sometimes what the integrated circuit does at the V out here, that is the time, sometimes the frequency gets doubled, or the amplitude gets doubled or such. Let's say this integrated circuit here, it would like double our amplitude. So let's draw some kind of really messed up. It's not the same frequency, but it should be there. So let's say, yeah, let's say that's what our IC does. It takes in this sine wave with this frequency and this amplitude, and it puts out this sine wave with this a little bit lower frequency. All this is bigger here, and this high amplitude. Let's say that is our function that our IC realizes here. And then the question is, yeah, I understand how 0.5 volts per microsecond, how it limits the linear rise of the voltage over time, but what has 0.5 volts per microsecond linear rise time to do at all with such a sine wave? And as we specified more clearly, what has 0.5 volts per microsecond do with the output sine wave? Because we're talking about the output slew rate here. So I write here slew rate. How is it coming into play? And then for some days I was on other topics and did not think about this one too much, but then at some point in time I came back to the topic, and it was really when in some YouTube video, somebody mentioned something very interesting. And the thing he mentioned, I want to draw here. So what he had also such a graph, and he had also drawn. Now let's make some more of a nice sine wave. Yeah, not quite. The valley here is a little bit too broad, but let's imagine this is a good sine wave. And then that person mentioned, hey, look at this sine wave. And look at how it rises and falls. Did you notice here at this tip point here, at the very tip here, it doesn't, for a moment it doesn't rise and it doesn't fall, just for a second moment. And at this point down here, it doesn't rise and it doesn't fall. And I thought, yeah, okay, so most probably it doesn't change. So it changes with 0 volt per microsecond, but just for a very, very short amount of time. It has zero change, 0 volts per microsecond, 0 volts per nanosecond, 0 volts per second. That's the change rate at this minimum point in time here. And then also here the change is 0 volts per microsecond. And then he said another thing, and I wondered, oh, okay, did you know, then here we get the change, we get a little bit more towards negative, and then all more negative. And the point, then I now wondered, and he said it, where is the biggest slope, the biggest change per time unit of this sine wave? And it's here, in this point here, where we cross the t-axis, on the x-axis, and here's the t-axis, the time axis, and here you have really the highest change here, so to say. And I don't know what it is here, and that is exactly the point. You have the change of voltage, you have all here, on all these points, you have a certain change per microsecond here. You can express this in microsecond. Perhaps between here and here it's only a nanosecond or so, but you can always convert it to the units, what change per microsecond. It's a simple physical units recalculation. You can always express it in volts per microsecond. And at each of these points you have a change per microsecond in volts, and it is the biggest change you have is here at this point. And also falling, and then rising also here at this point again. And if you value what your output of your component can support or can do, if it can support this biggest rise here, if that number is bigger than the rise needed here, then your output can follow this curve. And that's the first time, or that's my mental model at the moment. Please write in the comments or how you see it, or if I'm wrong here even, because that's just my own opinion. I didn't read it out of books, but I just imagined it like this when I heard all that. And then I started to realize, oh, okay, that number, it tells me what kind of sine wave I can support here. Because if you imagine now another sine wave, let's say, just for fun, let's say this would be at this point now 0.4 volts per microsecond, and here as a minus 0.5 volts per microsecond, and here it would be 0.4 volts per microsecond. So going down and up at the same rate, but just with different sign, here a minus, here a plus. And 0.4 volts per microsecond, if it would be that way, we can support that. We have 0.5 volts per microsecond. And I think slew rate is for going up and down. It just has no sign in front of it. But now imagine we had another sine wave. Imagine we had a sine wave like this, and the sine wave would go like this. So I'm gonna stop drawing until it gets even more worse. And And as you see, as you look at these points here where the t-axis is crossed, it's natural to be very steep here. It's much steeper than if you had just such a mild sine wave. And you have here an extreme sine wave, and an extreme change rate at the crossings. And of course, this would be not 0.4 volts per second perhaps, but let's say this would be, I don't know, 4 times higher. So this point here would be, so this here, this goes to negative. So this would be, let's say, minus 1.6 volts per microsecond. And here again, the last point here is also minus 1.6 volts per microsecond. So we would have such steep crossings here, the voltage changing so rapidly that 1.6 volts per microsecond, that we cannot support it. Our output cannot follow here. And what would happen then is the question. Perhaps, yeah, strange looking patterns would arise here. But then we wouldn't take that component. We would look for another component. Yeah? We would look for a component that can provide us the 1.6 volts per microsecond and not use this component. So we don't have to think about, oh, what would it look at? Just switch out the component. Use one that is really of practical use for your application here. Okay, but as you understand now, so this is kind of a qualitative thinking about it. And now the real question is, yeah, it's good that we talk about how it could look like, and yeah, the numbers are made up, it's no real numbers. But the cool thing is, you can, of a sine wave, you can easily predict what that, or you can easily calculate, that's the cool thing, you can calculate of a given sine wave what the maximum rise or maximum fall is. So what, and then when you have that, you can see, okay, is your slew rate good enough for that or not? Or is the slew rate not good enough for that? And the cool thing is, all of our signals that we deal with in practice in electronics, they have frequencies. So you could say, one could say, I have a voltage signal, and it has it goes from let's say plus 12 volts, from plus 12 volts to minus 12 volts. And so that's the amplitude, describing the amplitude, the min and the max values, and the frequency with a small f of my voltage signal is 1 kilohertz. That could easily happen in practice. 12 volt a signal going from plus 12 volt to minus 12 volt. The frequency of 1 kilohertz. So we can, yeah, so if we can imagine, let's draw it, for example. Here plus 12, here minus 12, and then going between plus 12 and minus 12. And just imagine that the units of the time axis are as such that this is a kilohertz. Plus 12, that should be. Okay. So how do you mathematically express such a sine wave? And I don't know, I write it down. I don't know if you know it. You can mathematically express that as the voltage depending on the time is, so the voltage, small v, depending on the time. Oftentimes you also have a u. Let's make a small v here. V of a time is, and then you write your amplitude, so 12 volts. 12, let's make it unitless for the moment, but you know it's 12 volts, we're looking at volts. times the sine of what? And often you see things like omega t, but the real but with omega we cannot work because we have a small f. And yeah, you need to know that omega, it is just another different writing for the frequency multiplied by 2p. So we can write that as v of t is 12 times sine of 2 pi times f times t. And yeah, and that is our description of our 12 volt signal, plus 12 to minus 12, with a 1 kilohertz frequency. And this one here, that's the description. So let's make that green. This one describes this situation here. And now the cool thing is, we do not want to have the curve itself, which is this equation, but we want to have the change of the curve in every point. And the real nice thing is in mathematics, there is a real nice way to calculate the change, and it's called the derivative. And if we can do that, we can say, okay, the derivative of the voltage over time is, okay, now the question is, yeah, how does one calculate that? And that's basic calculus. I won't go into details here. That is 12 times. So you derive the sine. Sine derived is cosine, and you let the thing in here be constant, and then so 12 times cosine times 2pft, and then you multiply it by the derivative what is in here, and the derivative of 2pft derived, clearly we derive, we want to know the change regarding to time, so this is simply 2 pi f. And so we have, if we multiply 12 by 2 and take this pi and f to the front, we have our change of voltage per time unit is 24 pi f, so we took that to the front, times cosine of 2 pi f t. Okay, and that is our change. So I make it orange here. So meaning, if we want the change at any point, like we said, we put in t, like here we have a value for t, we put it in and we get the change. So here's a downward change. And with this formula, we put in t here, and we get with the exact fall amount as the rate at which the function falls at this point. And what we're interested in is the biggest fall of this thing, or the biggest rise. And interestingly enough, the biggest fall, as we said earlier, is the function value is 0 here. Here, 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 and here. So where the function value itself is 0. So the function value itself is represented by this equation. And we have to ask ourselves, okay, where is this term 0 here? And so, and when we get that t, where this term is 0, then we put that t down here, and we have the biggest rise and fall of this plus 12 minus 12 and 1 kilohertz function. And we know if we have the biggest rise, then we can compare it to our maximum slew rate of 0.5 volt, and we can see if with this component we can support this function, this signal on the output. So let's do that. Let's first ask ourselves, okay, where are these points? For which t are these? Is this function 0 here? Which are these points? And in order to find out that, we must simply set this 12 times sine of 2 pi ft equals 0, because the voltage, it is then 0. Between plus and minus 12, it's 0. So let's do that. Let's say 12 times sine of 2 pi ft equals 0. Okay, first we divide by 12. Then we're left with the sine of 2 pi ft equals 0 without the 12. Now the question is, when is this 0? When is the sine of something 0? And the answer is, if this in the middle here is so if the argument of the sine is a multiple of pi. So but we're interested in only one place here. So okay, because if we have one place, then we have the slew rate that it takes, and that is all we need. So let's see. So for example, if the inner thing here is 0, then that would be one thing, because then the sine of 0, it would be 0. Or another thing would be at pi, so when that inner thing here equals pi, or when that inner thing here equals 2 pi, for example. So let's do that. Let's say, okay, this is 0 when 2 pi ft equals 2 pi, for example. So this is no equivalent transformation here, it's just an example. And when is that the case? When ft equals 1, or when t equals 1 over f. Okay, t equals 1 over f. And then all we had to do is take this t 1 over f and then put it into that formula, and then we would be done. We would know the slope. But even easier, I think, is to assume that this inner thing here is 0. So instead of going for this one, the inner thing equals 2 pi, we can go for the whole thing, 2 pi ft equals 0. Then, because 2 pi and f, they all are non-zero, then t must be 0. So that is even easier if we assume t is 0. And then, so we're taking now this point, t is 0. We wouldn't have to have calculated any long, because that's really an easy one. T equals 0, then we're just starting out, it must be the highest slope there. But we take the t equals 0 in that formula in here, and then we have v star of 0 equals 24 pi f times cosine of 2 pi f 0. F times 0, ft, f times 0. And yeah, so this 2 pi f times 0 is 0. this whole thing inside the braces here is 0, then what is the cosine of 0? The cosine of 0 is 1. And so we have v dash of 0 equals 24 pi f times 1. And times 1 you can just forget. That is just 24 pi f. And what is 24 pi f? So to say, 24 pi f, this is, so v dash of 0 is 24 pi times, and the frequency is 1 over 1,000 seconds. Just 1 kilohertz. No, I'm wrong. I'm sorry. That's not correct. So it's 1,000 per 1 second. 1,000 changes per 1 second. That is 1 kilohertz. So if we calculate that further, that just equals 24,000 pi, and then 1 over 1 second is hertz. But we stay with the 1 per second. Times 1 per second, and 24,000 times pi. What is that? Or we can do another cool trick. We can just do. We can divide here through 1,000 and here through 1,000. Even we want to have microseconds here down here, so milli-micro. So we can do divide by a million here, and we can divide by a million here. So we have 0.024 pi times 1 through 1 microsecond. And as you've seen, I decided to not put the volt behind the 12 in the beginning, but now it would be good if you write it down again. You heard me when I said, hey, we don't want to write 12 volts here, so no V here, but now it would be good to have it again. So it would be 24 volts here, then 24,000 volts, or 0.024 volts, but we also can write it here then in the numerator. And you see already we have volts per microsecond. This is exactly what we wanted to have to compare it with the 0.5 volts per microsecond. Yeah, and then let's see what that is, 0.024 pi, and that is around 0.075 volts per microsecond. And as you can see, that is easily, so 0.075 volts per microsecond is easily less than 0.5 volts per microsecond. So we can easily support that 12 volt signal with our 0.5 volts per microsecond output slew rate. And that is how the calculations are done. Another question is, okay, with what 1 kilohertz we can support, but how far can we go? How far can we, what higher frequency can we support? Can we support 10 kilohertz, 100 kilohertz, a megahertz, a gigahertz? What can we support? So it is quite clear that also it depends very well on if we're going to 12 volt and minus 12 volt, or if we're just going to like 1 volt and minus 1 volt, because the curve will obviously be not so steep If we just go to 1 volt here, you can imagine that's a smoothened curve, that's smaller, flatter curve. But yeah, in the question of with this 12 volt situation, how far can we go? But I will make another video about this. This is already complex enough, and I hope you can use that and it will be useful and you like it. And please give me now a thumbs up if you like it, and subscribe if you want to see more. And yeah, we'll meet in the next video. Thank you, and good night for me. Good night for you, I don't know. Good day.